Hello and good morning, explorers. Welcome to Reach the World's Explorer program. For 25 years, Reach the World has inspired youth to become curious, confident, and compassionate global citizens through virtual exchange. My name is Tim, and you have arrived at the second live event with the Tyrrhenian Continent Ocean Transition Expedition. Explorers Tessa and Larkin will be joining us today from the scientific drilling vessel JOIDES Resolution, which is cruising off the coast of Italy in the Tyrrhenian Sea and collecting rock and sediment samples from various points beneath the seabed. We have already learned a lot about life aboard the JOIDES Resolution through the virtual exchange articles published on the expedition's homepage. And you can see the link to that in the chat if you haven't already seen it. And today is the moment many of you have been waiting for. We're going deep into the science, and we will see exactly what happens to a core sample from the moment it's pulled from the sea and brought aboard the ship. I am excited to see it, and I know you are too. Special welcome to the teachers and students who are joining us live today or will be watching this recording a bit later. We've got an amazing group from Kittredge Magnet School in Atlanta, Georgia. Hey, Kittredge, joining us backstage. We'll bring you on in a little bit to ask your questions. Falmouth Elementary School, Sharon Elementary School, United High School, Franklin L. Williams Middle School, Palmer Public School in Nebraska. We're so glad you're joining us today. For those of you who are joining in via YouTube, please feel free to use the YouTube chat bar to let us know you're here, where you're joining from, and of course to share any questions you have for Tessa and Larkin as we go. We'll get to as many questions as we can in the next 45 minutes, but we have a lot to cover today, a lot of exciting things to learn. So are you ready to travel virtually to the Tyrrhenian Sea and the JOIDES Resolution? I sure hope so. Let's bring Tessa and Larkin onto the screen. Hey, Tessa and Larkin.
Hello! I'm Tessa.
It is
I'm
wonderful. It's wonderful to see you. You seem very happy today. I think it has something to do with all that Italian sunshine that I see shining on your helmets and your faces.
Here with you all and show you more about the lab and the core flow. But just quickly, right behind us is the Tyrrhenian Sea. This is what's good. Oh, no. Oh, wait. Oh, yeah. Sorry. The screen changed and I panicked. It's the Tyrrhenian Sea. But we're going to walk over to the rig floor to tell you more about how we get a core and what happens after we get a core. So okay, here we go. Yep.
Fantastic. Tessa and Larkin, as you're walking, I would like to bring up a map of where you are, just so we have a good sense of where you are. We have this wonderful map with a hand-drawn arrow that shows where you are, right off the sort of western side of that boot-shaped Italy. You can see more or less where the ship is and where Tessa and Larkin are joining us from right now. So that gives us a sense of where you are. I'm going to turn things back over to you.
Awesome. All right, can you hear me loud and clear?
Yes, we can hear you very well.
Good. Okay, great. All right. So welcome to the JOIDES Resolution. Is it?
There we go.
Okay. All right. So first, I would like you to take a look at our beautiful derrick. She is 200 feet tall, 70 meters tall, and she's how we are able to collect these sediments. I also just want to tell you really quick how we're able to stay stationary. It's called dynamic positioning, which means basically in a nutshell, we have 14 propellers working together on this vessel to keep us from going too far forward, side to side, or back. So we're nice and stable. Let's go. All right, so it takes us about 12 hours to what's called trip the pipe all the way down to the ocean floor and 12 hours to bring it back up. Right now we are bringing the pipe back up, and I'm just going to walk you through really quick the steps that takes. From over here is a good angle. So you can see where right now we've got the pipe up, and they just unscrewed it, so they just loosened it up, and now they're going to have these arms come out, go around the pipe, and then it's going to be able to pull it back. There she goes, and they're made of iron, which is a nice flexible metal, which is really important when you're underwater and you're trying to, sometimes you just see a little flex, right? And just for time, so you can see it going down, and you can see the bend in that iron. Each one of these are 33 meters long, or about 100 feet long. And here she comes down. These arms are bringing her down. And that's the end. And then the process is just gonna go over again. But because of time, we're gonna move on through. Now, the sediment collection is going to come in tubes that are these long plastic tubes. These are going to be inside of the cores. What's going to happen is when they bring the collection up, or they bring the sample up, there's going to be 5 people standing here waiting to get that sample, because it could be filled with sand or rock or sediment, heavy materials. And so what they're going to do is they're going to wait until these guys bring over the sample, and then they're going to carry it. And what we're going to do is walk down this, what's called the catwalk. And as you see these are all little. Well, we're gonna be setting it down on these racks. So they're carrying until we get all the way down here, and then we would set it down. So if you can imagine that each section is going to be about 9.5 meters or 30 feet long. And I'm going to grab a little sample. This is a very small section. Normally, as you can see, they would be this long, but you can't work with something that long. You need to break it down into a smaller section. So what they would do is they would bring over, they have over that long pipe, remember, and they would bring over a ruler, and they measure out 1.5 meters. They mark off 1.5 meters, and then you take this really cool tool, which was actually invented here on the ship. So sometimes when you're working on a ship, you don't have everything that you need right at the ready. I mean, we're kind of like a city out here in the middle of the sea. So sometimes you have to get really creative and create your own things. And that's why it's so nice to have these engineers on board and all these materials, like even a 3D printer, to create these things. So what they did was they were able to put a blade in here, and this just encloses around the tube, and then we cut. So now we would have 1.5 meters section that you would take. It's very important to know which way the core, like if it was facing north or south, up or down. So on the top you put the blue cap, and on the bottom we would put the white cap, and then we would take it inside for further to be able to test it and to mark it. Now I'm going to move on to the drills, but I'm going to turn this Bluetooth off because I think they'll be able to hear on the iPad. Okay.
All right, so these are our drill bits. At the end of the pipe, we use these drill bits to be able to make the bore hole. So the seafloor is completely covered, and we have to make the bore hole so that we actually can start collecting the sediment or the hard rock. This silver one is the sediment or the soft sediment drill bit, while this one on the right is the hard rock drill bit. They both have slightly different features. As you can tell, this one seems a little bit wider than this one because the formation of the seafloor plays a huge role in how well we can get samples back up to the ship. So if we know we're going to be drilling in a soft sediment location, we're going to be using this drill bit. And the core liner that Larkin was telling you about goes in the middle of the drill bit because the rotary cones make the bore hole, and everything that is not on the wall of the bore hole goes straight into the core liner. Same thing happens for the hard rock. Anything that is not the borehole wall goes straight into the core liner that's behind these rotary cones. So when we are getting ready for an expedition, a group of scientists and expedition logistic managers come together to actually decide what places are more fruitful or useful for the science that wants to be done. So for instance, for this expedition, the sites were chosen about 5 years before the expedition even started. So let me change my camera so you can see me. So it was 5 years before the expedition even started, and then it was 1.5 years to confirm if those locations are still okay to go to. For instance, one of the locations we wanted to go to, we learned just recently that they had just put down internet cable lines across that area, so we no longer could go back to that area. So we're constantly thinking about where are we going to go drill, and where can we still go drill. We even meet with environmental protection departments to determine, hey, is it still okay? Are there any marine mammals that we have to be aware of that use this area, or any other marine life that might be using that area? So we work with environmental protection departments closely, and they will confirm or deny access to certain locations. So we come to the expedition basically knowing everything we can do, can't do, and where to go and when to go on the expedition. All that decision making is made beforehand. So now,
oh yeah, we did tell them why we chose this place in particular.
Go ahead.
Okay, so the reason that we chose this space in particular was because we have seismic evidence showing us that the mantle is more intact here and more exposed than in other places in the sea. And what that means is, so if you look at my fingernails, normally the tectonic plates would be like so. But as I'm trying to get in front of it,
you got it.
But there was a shift that happened about 5 billion years ago, pulling the crust apart, and pulling it apart so much so that it almost became like a cap, and it tore. And when it tore, it started to expose this mantle more. That's really important. That's what we're looking for, is this intact mantle. Another thing that is important here is that it's a young sea. So the Tyrrhenian Sea is younger than, say, the Atlantic, which is about 145 million years old. We're looking at 5 to 15 million years old in this area. So that means that there's less sediment collection. Sediment collection is very important because the thicker the sediment layers are, the harder it's going to be for our drill to work to get to the mantle that we want to get to. So that's another reason that why we came here, because it would take a lot less time to get to the sediments that we were trying to get to. There was a fact about New York City.
So the reason getting mantles quite important is because generally under continental crust, so all the land that we live on, so my land back in Boston or my land back home in Brazil, all of that can be like 30 kilometers deep before you even get to the start of the mantle layer. But because the tectonic plate in the Tyrrhenian area pulled at itself and stretched the land under the sea, so the sea floor, it actually got really, 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 really thin. So it became 300 meters below the sediment instead of 30 kilometers below, which makes it much quicker to get to, and it saves us time, because 2 months at sea sounds a lot, like a lot of time, but it actually isn't. We go through all our logistics quite fast, and we're always racing to get to the next location on time. But let's show you what happens to when we get a sample, because that's what we're here to talk about. So this is our lab inside. So once the rig floor crew get us a core and the marine technicians cut up the core, we come into the physical properties lab, and this is what a full core could look like. So blue indicates that that's closest to the sea floor, and then white would be at the end of that area, that tube, to show you that's the most bottom part of the core. So that's a whole round. When the whole round comes in, it gets laser engraved, basically getting a label on the plastic, and it's hard to see, so it's hard for me to show you an example, but you can feel it. So there is a tube in there, and you can kind of see the harder parts of the plastic. That would be the laser engraved part. And that's really important for us to be able to identify which part of the core is the archive half or the working half. So it gets laser engraved, and then it has all these physical property measurements like the Wormsole. I always have fun with these names because I always think they're pranking me, but it's actually, the name of the machine is the Wormsole. It is the whole round multi-sensor logger. And one of these is called the P-Wave, which is this one. One works on magnetic susceptibility and one works on measuring density. And Larkin got really excited about the P-Wave.
Yes.
So do you want to tell us about the P-Wave?
Absolutely. Okay, so the P-Wave is the best. Okay, so when we're doing these running the seismic evidence, and with these ships, there is a, on the bottom of the ship, they send out a sound wave to record, to kind of map out what the bottom of the sea looks like, the sea floor. And depending on what kind of surface you have at the bottom, it's going to ping back a different residual, like a different image.
A reflection.
A different reflection. So for instance, imagine if you had a tennis ball and you threw a tennis ball into a wall. It would bounce right back, right? So that's sort of what's happening here, but with sound waves. They're pinging something off of the bottom of the ship and it hits the sea floor and it pings back a certain way. It would be much different if you took that same tennis ball and you threw it into a mattress or a pillow. It would absorb that pressure, and it would instead of bouncing back a really high definition reflection, it would turn back a softer reflection. So then you would know that you're dealing with more of a soft sediment and not a hard sediment. And so what's happened is over the years we've mapped a lot of the ocean, we've mapped some of the ocean floor, and what this is able to do is when we go back to those areas that we've mapped, we can now pull an actual core from that and measure that P wave. Now that's important because now we can fine tune the information that we already have. So say we thought that something was, I'm just going to throw out a number here, like 200 feet, right? But we do this and we run it and we realize, oh, we got that sediment at 225 feet. So it's a little bit different. So really we're just fine tuning things with this machine.
So basically we shoot sound from this side and the sound picks up on this side. So how fast the sound moves through it helps us get a velocity number for that material. That's really important for, like what Larkin was saying, ground truthing or verifying we measured the seismic correctly. Then we would come through the rest of the lab to, let's say, the X-ray machine. And this X-ray machine is quite awesome because we had an older one, but it could only get one 2D image of the core. And it's essentially the same as when you break an arm and you want to see the inside bones of your arm and just see how bad you broke it. Same thing here. But instead of seeing a bone, we're trying to see what's inside the core. Where did it break as we were drilling? Or are there any interesting things in it, like potentially wood chips or rocks that aren't usually in sediment, or pebbles, or sometimes bigger than microfossils, bigger fossils than microfossils. Yeah, so for instance, the core would go through that hole, we would close it, and then this machine would run across the core and develop an image on this computer. Let's see if there's an image already open. Yes, perfect. So this is an example of what you would see when you look inside a sediment core, and you can tell any whiter color means more empty, less dense. Any darker colors mean more dense, more stuff is there. So all of these white little lines tell us that there's many fractures inside the core, or many fractures that are filled with lighter material. It doesn't necessarily mean it's empty. It just means that there's something that is less dense than the area around it. And we can even see the layers that exist in the sediment, meaning there's heavier material in that one layer compared to the lighter color around it. So that's what the X-ray can look like. Once we're done with a whole round, we'll go to the splicing room, which has the super saw and the wire cutter and other saws.
And tiny cups right now.
And tiny cups. Do you want to tell them about the cups?
Yes. So when we're sitting down, when we have we have a re-entry, what's called a re-entry cone, and that re-entry cone looks almost like a bullseye. It's a big cone shape at the bottom of the sea. Well, what happens is when we're sending the drill pipe initially down, we sometimes send a camera down to find this hole. It makes it easier to find this hole that is at 3,500 meters down the ocean floor. While we do that, we also put a bunch of styrofoam cups in there, and we decorate the styrofoam cups in fun ways, color them, and put little images and things on them. Because what happens to these styrofoam cups when they go down, that air pressure squeezes all the air out of these cups.
So water pressure.
Water pressure squeezes all the air out of these cups and then makes them little tiny, almost like little toy cups.
So to give you an idea, the cup used to be as big as Larkin's hand, but on land, like on the ship, we sent it down and all that weight of the water squished it into a smaller cup. So now we get to have a souvenir. Mm-hmm. But this is the track. Yeah.
Normally when it's not set up for tiny cups, when we're actually getting cores in, right now we're gearing up to get samples, but so it's a little bit slower in here. But normally we would take the whole core, and we would place it onto this tray, and this is our super saw comes through, and it can cut it in half.
Yep, kind of like you see in this picture.
Yes.
This is a half core where they're setting up the whole rounds to be cut in half. Go ahead.
If there's smaller sections too, they have smaller saws.
Go on that side. Oh, yeah, there you go.
Yeah. For like smaller, if you have like a smaller rock sample or something, you can put it through these smaller saws.
Tim, I think I sent you a picture of one of the cores if you wanted to share screen to
Yes.
show it.
Let us bring that up. Let me find it on here. You gave me a picture of, okay, we've got a little bit of a demonstration of what the drilling apparatus looks like here.
Yep.
The drill, there we go. We have a sample that's fresh off of the seafloor.
Mm-hmm.
They're cutting it.
Cutting it.
Oh, and that's a reefer. Maybe I didn't get a.
Yeah,
Maybe I
I'm
didn't.
gonna just, there we go. No, I see it.
There it is. So this is an example of when you have a whole round core sediment that got cut in half. So now you can see inside that whole round, and it's now called a section half of the sediment core. Right next to it is, on the left side, is a section half of a hard rock core. So depending on where we drill, we might get both sediment and hard rock, or maybe we stop drilling before we get hard rock. It all depends on the goal of the expedition. But that is what a section half of a sediment core could look like. But I do have a section core out right now.
Can I, Tessa and Larkin, sorry to interrupt, but I see a student who looks like she would like to ask a question. So do you mind if I bring her up? All right.
Of course. Absolutely.
Let's go to Kittredge Magnet School. Thank you so much for your patience. And please go ahead with your question.
Do you see a large variety of sediments?
Yes,
Absolutely.
so much. Such a variety.
You'd be very surprised at how big of a variety we find at the bottom of the sea.
So the variety can come from texture, like how sandy it is to how muddy it is. It can come from color. So I've seen green, I've sometimes seen blue, I've seen red, orange, and even black. And sometimes black can indicate ash. So maybe volcanic eruptions happened in the area. So there's huge variety. And what's awesome is sometimes Lark and I are like, oh, is this question, like, is it weird to ask why it's blue? But I'll hear a scientist go like, why is it blue? So then like all of us keep getting surprised by what we're pulling up from the ocean floor. So that's the importance of getting actual samples, because you can verify, like, is it blue or is it gray? So yes, there's a lot of variety.
Fantastic question. Thank you. I'm going to bring up another student at Kittredge who is waiting patiently for ask her question. Go ahead.
So you said it takes like 12 hours to get this core all the way down and 12 hours to take it back up. Can you drill multiple cores at one time, or can you only drill like 2 a day?
Yeah. Do you want to take it? Do you want me to take it? Go for it. Okay. So just to be clear, so there's like multiple things happening when we're drilling. To build the pipe, it's 12 hours. But we send a secondary barrel that's smaller than the pipe through the pipe down. And so to get an actual core, if it's sediment, can happen almost like every 30 minutes to bring it back up. But if it's a hard rock, it can be as long as getting a core every 8 hours, depending on how hard the rock is. So we don't drill multiple holes at the same time, but we can send a barrel down, core, bring it back up, and then send a new barrel back to back down as we take the other core. So we are constantly sending a barrel down to get the core and bring it back up. Okay. Then once we're done with one borehole, we can create a new one, but we're never doing 2 at the same time.
Okay, yeah, that makes sense.
That's a great question.
Yeah, fabulous
but you're
question.
not wrong. There are other drilling ships that can only do sediment that send that almost like send a 3-prong thing down for really, really shallow waters. So you are thinking of something that exists on another ship.
Fabulous question. Comments will come right back to you. I'm going to switch over to the quasars. Go ahead.
What problems do you face when drilling the core samples?
Sometimes it could be a multitude of things. I mean, we could have rough weather, which would cause the ship to. We do have dynamic positioning, which normally keeps the ship into one place. But if we come into rough seas, we might have to shut it down for a little while and wait till the weather passes, or the seas calm down. Also, depending on what kind of sediment we're going through. If we're going into hard rock, that hard rock can hurt our drills. Our drill bits are very strong, but they're not invincible. And so sometimes you can have drills that actually we have things it can break sometimes.
It can break?
Yes. So a multitude of different things can happen that cause delays in getting these samples.
Yeah.
All right. Excellent question. Thank you, quasars. Back over to the comments. Go ahead.
So how long does it take you to analyze a core?
How long does it? So you kind of want to break the core up by the expertise that you have on the ship. So, for instance, this is a funny picture. Everyone started drawing on it. Hold on, 1 second. Ignore the drawings. But this is my easiest access. But these are all my scientists. So, for instance, Walter, you read about Walter. I'm gonna stop showing you because of the images, but Walter is a sedimentologist. So for him, he will get a sediment core like as soon as we start drilling, because sediment sits on top of hard rock. So he can get a sediment core within 20 minutes, and then he can get a sample within 5 minutes of getting that sediment core. But a hard rock, they have to wait till we get through all the sediments, and then we have to start drilling the hard rock and bring that back up. So maybe what it took the sedimentologist 30 minutes to get a core, they will take 2 hours, 3 hours. But once they start taking a sample, so they'll have the core, maybe they'll take a sedimentologist will take a toothpick amount and look at it under a microscope. Again, that's like 5 minutes, 10 minutes. But a hard rock person, they might need to choose a part of the rock, have that rock sliced up into a cube, have that cube be polished down into a very thin slice to then be put under a microscope. So they might take a day before they can start looking at that sample. So it really depends on what you want to do with that sample, where the process might take longer.
Nice question.
Thank you. Question.
Fabulous question. Yeah, why don't we do, I see we've got another student over on the KSR side. We'll do like one more round of questions and then we'll continue with the tour. And before we bring up our next student, I love the description of a scientist as a hard rock person. I envision them like listening to music while they're doing their work. All right, with that, let's turn it over to our next student question.
What's the most interesting thing that you have learned about volcanoes?
What's the most interesting thing that we've seen out here?
Learned about volcanoes.
Learned about volcanoes. Ooh, I have volcanoes. We've seen evidence of volcanoes. Let me run over to my sedimentologist. Hi, sedimentologist. So we just got a question about what's something interesting we've learned about volcanoes, and I think you guys have seen some evidence. Could you talk about what you've learned about the volcanoes in your sediments?
Yeah, I mean, the volcanic eruption, it's still a matter of debate, right? Because we see volcanic material in the sediment, but like at this stage, we are not able to understand, for example, where it's coming from. So there's like potentially two ideas, two options, either proper volcanic eruption, and then you got like ash and a pyroclastic flow going on the ocean and falling. Or maybe there's a volcanic eruption, and instead of ash and flow, you've got lava, and then this magma and lava gets eroded, and then the sediment can come from there. So it's still a bit uncertain at the moment what happened there, but the thing that we know is that at some point there was a flux, a current, bringing this volcanic material, which is a bit still uncertain where it's coming from. And the cool thing is that there was a current, and we can see it here. And now, like when we get on shore, we start investigating this more. Yeah.
Great. Let me just show them what you're pointing at.
Yeah.
So this is a sediment sample that they took a toothpick amount from the sediment core and put it under the microscope. And what is the volcanic part?
Yeah, this is the volcanic glass. It means that like there was an eruption or something, and the crystallization it got solid like very fast. So there was no time for the crystal to grow a lot. So it was very fast. So it's almost glass, and that's the only thing we know so far. And the other thing is that we can find it here along with those fossils, which are like ex-living organisms within the water column and the seafloor. So there's a little bit of a mix, and that's very interesting.
Great. Thank you, Luca.
Thank you.
Yeah, fantastic question. Thank you very much. I see one more student standing up. We'll take one more question, and then we'll keep going with the tour. Go ahead.
Hi. Have you found anything new so far?
New?
Yes, like any new plants?
Yes. This expedition has been really awesome because, like I was saying before, with the sediments being a different color, a lot of the scientists are surprised by what we're pulling up at, like the layering of certain rocks with each other, or the layering of certain sediments with each other, like the textures, the colors, the types, the minerals. So there just seems to be a little bit more unexpected material showing up in what we thought we understood about the Tyrrhenian Sea. So for instance, like we're finding like glauconite in a layer of sediment where we didn't think we would find glauconite, which is just a mineral that's green. So, but we did find mantle rock, which is what we came out here to find out, but we're learning about what made that mantle go through its processes where we thought the process wasn't happening at that age. So it's a little bit of different things, like smaller actions that we're finding new about the mantle or the sediment, which basically answers the biggest question: how did the Tyrrhenian Sea open and what happened? And they're actually getting a really big picture of that from the mantle rocks.
And many times when we come out for these expeditions, you come out with a question or a few questions, but then, and as you learn, as you solve those questions, or as you get the answers to those questions, then more questions arise. So it's just this constant learning process out here.
Yeah.
All right. Thank you for that wonderful question. Can we continue on the tour? I know there's a lot more to see, so I'll turn it over to you.
Awesome. All right. And then let me just put it back on my back camera. So we brought the section halves out, and they get put onto the working table where we have little flags for each scientist to identify what part of the core they want to take more samples of. So for instance, Osh decided to put his face as his little sticker to say which part of the core he wanted to take. We have this side to show an archive half. Archive means that we cannot do anything to this core except look at it and use our eyes. So for example, there we go. For example, this is a core that is a few million years old, and you are sharing this experience with me, seeing sediment that hasn't been seen in a few million years. And so what they have to do is only use their eyes. What does this look versus that, versus that, versus this, versus that? And they have to measure along this ruler where they're seeing that color, where they're seeing that texture, or any unexpected items. Let's say like there's a rock in the middle of sediment, or a fossil, or something like that. So this is the archive half. We wrap it in plastic because we try to preserve the open core from our air and our temperature and our moisture and our humidity. So we wrap it in plastic and then store it in those plastic tubes back there. Yeah, we can learn. So there was a picture that Tim showed that, Tim, if you want, you can show right now. Again, it's with all the red caps and the black caps before this picture. There you go. That is our repository. That means we have 3 big libraries around the world, one in Japan, one in Germany, one in Texas, that stores all the cores that have been collected since 1970. So you, if you're interested in looking at the cores, for maybe you want to do some research or ask some questions, or your teacher wants to pull some examples, can go look at these cores and do some sampling. And that's the purpose of these repositories, is for that future generations can come back and do more research on these cores, even when the expedition has already finished. For example, Luca, that you saw earlier, has looked at cores from an expedition that happened in 1988. But he's not as old as 1988. He wasn't on that expedition, but because we have that repository, people can go back to it, which is really awesome.
The repositories are amazing. I got the chance to go to the one in Texas, and it's just floor to ceiling samples for aisles and aisles and aisles. I felt like I was in a Harry Potter movie, except instead of like books, it was all these sediment samples, and it was amazing. It was this huge refrigerated warehouse just full of samples.
So let me jump back. So we do archive. They'll get imaged here. So the archive house will be imaged with this high resolution image that basically is a camera that takes at every millimeter or quarter, eighth of an inch every image of the core. So we get a really high resolution. We'll also use this imager to take, not take pictures, but visualize the color value in the core. So for instance, your blue might be my green. So we have this machine here to give a number to the color. And so even if I say it's blue and you say it's green, we both are saying it's that same number because we have this machine to give us an objective measurement of what's seen in that core. Then section halves will be sent over to the paleomagnetism area, which is, we have a section half magnetometer that basically sends the whole section half through this giant magnetometer, which basically measures the magnetic signature of the, exactly what you're seeing right now. This is not a section half, but it is what happens. It goes in and out, in and out. So essentially it has these two magnet measurements right here, and they'll measure a signature here and a signature there along the section half to give us an idea of when these rocks or sediments were forming or laying down. Where was the North Pole? Where was the South Pole on the Earth? Because the North Pole and the South Pole changes every so often, and the paleomagnetist is able to look at those numbers and say, oh, this sediment rock sediment was laid down at this time because that's when we have this reversal, and this is the graph that he looks at. So he knows the numbers for the black areas, the white areas, the black areas, the white areas. And if a sediment or a rock comes back with a number in any of these areas, he can tell us, oh, okay, the rock is this age or the sediment is that age. And then once he does that, he works with our micropaleontologist on this side, who basically looks at fossils that kind of look like this. These are the colored versions of the images, but they usually come out very gray. And they can also compare when these fossils laid down in the sediment and what age they are. And that helps us get two different measurements for what we think the age of the sediment or the rock could, sediment could be. We can't use microfossils for hard rock cores, but we have multiple scientists working on doing that. This other area is the microscope area, which Tomo, who is waving, is our igneous petrologist. He looks at rocks. Tomo, can I just show them what you're looking at?
Sure. Okay. This is the not thin section. What thin section?
I did not talk about thin sections yet.
Could you explain then?
Okay, so this is a thin section. So what that means is, remember when I was talking about how earlier a hard rock scientist would have to get a cube of a rock, slice it down, polish it, and make it really thin? This is what that happens, what it looks like after. So this is a very thin amount of rock, and then he will put it under a microscope.
And then that thin slice allow the light passing through here. And then what we see now is the microscope image of the thin section. And then I can show you more.
Yeah.
Slide.
The more exciting part is we can see colors. So when you change the light, the direction of the light that goes through this thin section, you can get better imaging of what mineral you're looking at that's in the rock. And why does it, when you turn it, what do you learn from when you're turning the section and these colors are changing?
So we can identify this color, and when this color going to dark, we can identify what kind of minerals here, and then what other minerals are, and then what the kind of relationships between this mineral and surrounding minerals, which tell us a history of this rock itself. Yeah.
Awesome. Thank you, Tomo. So he's our hard rock scientist, which we call a petrologist. And then Luca, that we talked to earlier, is a sedimentologist. So the sedimentologist does not look at the thin section for their sampling. He looks at the smears, which we saw an image. But this is one area. Hi.
Oh, sorry, you've got a special guest.
Oh, I got it. No, it's okay, Tim. Go ahead.
Okay, I just wanted to note that time is flying by. This is so fascinating. We have a student who's been waiting very patiently to ask a question, so I want to bring her on and give her a chance to ask her question.
Sure.
All right, go ahead.
What's your favorite part of your job?
Ooh, I'm gonna have Brandon answer this. So Brandon works on the ship.
Hi, everyone.
What is your favorite part of your job?
Ooh, favorite part of my job. I like being able to go out on a ship and work with other different scientists from different countries and getting to do science with all these different people and work together to understand how the Earth works. So I really like the aspect of exploration. We're going out into the middle of the sea. We don't know what we're going to find. And it's a really fun part that keeps me happy every day, just the excitement of what we're doing and what we might discover.
Great.
Nice.
Thank you, Brandon.
Thank you.
Excellent. Tessa and Larkin, how about you? What's your favorite part of your jobs?
I mean, Larkin and I were just talking about this earlier. We really like the fact that we can keep talking to all the scientists and like learn from them. So like I get to learn about mineralogy and petrology and sedimentology and fossils, and just like be able to talk to them and learn more from them, and then tell you all, because that's the most exciting part for me.
My favorite part of the job is seeing these, because I think of the scientists as kind of detectives, and we're all trying to solve this mystery, right? So when the scientists all come together and they compare notes, seeing things being solved in real time and new discoveries happening in real time is so exciting.
It's really special.
And like Tessa said, being able to take that information to you all is even more exciting. So being able to share this with the world and to get you all excited about science the way that we are excited about science is one of the best parts.
Excellent. Well, thank you. Thanks for that great question. As a little bit of a time check, we have like 5 to 8 minutes left. Is there anything else you urgently want to show us? We could save the second part for a future live call if
Yes.
it's too much to tackle in that amount of time.
Well, I do have a scientist with me, so I'm happy to take more science questions.
Fantastic. Well, let me put out the call to our Kittredge students, and I see somebody stepping up. Fabulous. If you have any questions you want to ask, we've got a great team who's ready and willing to ask them. And I have a couple questions I can ask on behalf of students who are going to be watching later too. But we have a student ready to go, and I will invite her to go ahead.
Let's say it's raining really hard. Like, how does that, like, does it like stop you from getting core samples?
Yeah, so if it's raining really hard, no. But if with the rain comes waves that are higher than 4 meters tall, then yes. So we have a compensator on the drill floor that will actually move the ship up or down with the waves so that the pipe itself doesn't move. So it can only go up 4 meters or down 4 meters. So if the rain makes the waves higher than that, so 5 meters, 6 meters, then our captain will actually call the rig floor and say, stop everything, we have to pull out, so that the ship does not get hurt or broken from those waves moving the ship. We need to be able to move with the weather rather than move against it, if it's more than 4 meters tall.
Fabulous question. Great. We're going to go kind of rapid fire here. I'll switch over to the comets. Go ahead, comets.
Is there anything that you want to see in the sediment?
Yeah, so in the sediments, we're looking for lots of different things. One thing that we're looking for are large debris flows or deposits that are formed that are high energy. So these could potentially be associated with volcanic eruptions or tsunamis that may have happened in the past. And so we're trying to understand in the sediments how those are deposited and the record that they provide of those past events. And this could help us better understand landslides and other parts of the margins and the hazards that they might provide if one of those events were to happen in the future. That's one thing that we're looking for. I think that you got to talk to the paleo team. They're looking for how life has evolved on Earth and reacted to different environments through time. So how ocean circulation in the Tyrrhenian has changed and affected different species that live within the ocean. So those are just a few examples of some of the things that we're looking for in the sediments in this particular area and on this expedition. Great question.
Another fabulous question. Kittredge, you're on a roll. I'm going to move the comets backstage and move the Quasars back. Go ahead with your question.
By having access to all the core samples, wouldn't that mean you have the information of like the area that you're drilling from?
So when you say access to all the core samples, you mean the ones in the repository?
Yeah.
So the repository actually holds all the samples of core from expeditions that have gone around the world. So we've had expeditions in the Pacific Ocean, in the Antarctic, in Indian Ocean, in Mediterranean, in the Arctic, near Greenland, near Brazil. So we've actually only, we only had one other expedition in the Tyrrhenian, right?
Yeah.
So why
Maybe
two? So why do we need to come back?
Why do we come back? Well, this is an exciting area for lots of different reasons. In particular, one of the goals of this experiment is to understand the difference between continental and oceanic crust and what are the rocks that make up the ocean floor. And this area is unique because it recently went from continent into ocean. So we had a new small part of the sea that formed here, and it's exposed. So the rocks are carried up to a very shallow depth where we can access them. And in particular, one layer of the earth that we don't know much about is the mantle, which is typically hidden beneath the crust, the outermost layer, and we don't have access to it. But in this area where we are today, it's really special because that mantle, through stretching of the crust, it's basically been uplifted and exposed so that we can actually access it and drill it and get those rocks. So that's one of the really exciting things about the place that we are today, and a unique geological setting compared to other places on Earth.
So when we came, even though we've been here before, that didn't have enough of the samples to actually answer these questions.
Yeah, that's right. A lot of the drilling expeditions in the area before were targeting a different event that was contained in the sediments, where the Mediterranean Sea started to dry up in the past, and basically all the water started disappearing from it. And this is a really well-known, famous event, and a lot of the past events, drilling cruises focused on that specific event and less on the drilling the mantle rocks, which our cruise has been focused on here.
All right, fabulous. Great question, great answer. Thank you so much. I see maybe one final question from the comments, and I will give you the honor of the final question for today. Everybody on track. I don't want to keep our students from their next class.
So, what type of fossils have you found in the core samples?
Ooh. No worries, Brandon doesn't know that. So the fossils we have found are called microfossils and nanofossils. So Tim, I think I sent you a picture of one of the microfossils images.
Yeah, I'll try to bring it up here.
So microfossils are extremely microscopic. So here, this is what you see under a microscope. Depending on the shape of these fossil shells will indicate a species name. So like the name of that kind of organism. So the micropaleontologist will try to identify what these are based on the shape of the shell. I am not too familiar with the names, but they do change per layer, and they identify a certain age because they only exist for a certain amount of time. But Tim, if you move to the next slide, so here's an image of a microfossil, one of the species, but you might see in the top cone, the dome of this microfossil, there's a tiny little star in one of those pores. Can I draw on this? No, I don't.
I don't think so, but I can see the star. You had a great description.
Yes, that star is a nanofossil. So my nanopaleontologist only studies that tiny little fossil. So we have living organisms that live in our ocean that are even smaller than the microscopic organism that we're seeing here image. So by looking at these two fossils, the two paleontologists worked together to understand age of the sediment, because when they died, they fell down with the debris in the ocean at that time. So I don't know the names. Right. They do have really fun names that are really, really long. Which could be but the JOIDES Resolution webpage has a poster with all their names. So feel free to get that poster if you want.
All right, great. We'll share the link to that. And Kittredge, if you are not in any hurry, I'll keep asking questions all day. But you'll have to let me know when you need to go. I'm going to bring our K-stars back up. I see a student ready to go.
How do mud volcanoes differ from regular volcanoes?
Hold on. How are mud volcanoes different from regular? Okay, so like Walter's description in that blog, mud volcanoes are the ones that only spew out the mud, while regular volcanoes spew out the magma. I have another volcano question. So I made a blog about Walter, and he talked about how he studies volcanoes that spew out mud, so mud volcanoes instead of magma volcanoes. But can you talk more about how those are different from each other?
I'm not an expert in that, and
Walter's asleep.
Walter's asleep, but I guess maybe it's obvious, but the material, the composition of the material is different because so if it's a mud volcano, the mud component is predominant, so it's like a more sedimentary style of deposit, whereas like a classic volcanic deposit is characterized more by igneous component instead of sedimentary. Probably it's volcano because it's the same type of style, but the actual deposit has different composition, I think.
Okay.
Maybe Walter can answer that.
No worries. Too bad Walter's asleep. So we all work 12-hour shifts, and Walter is already asleep. This is in the middle of his night. But I think it's just the different origin of where magma would come for a volcano. There's mud for the other one.
All right. Yeah, that's a good point. I know lots of questions. We had a lot of questions for Walter, but Walter does need to sleep sometimes, and this is his sleeping time. We can pass those along. All right. I keep saying we're going to have our last question, but Comets, you look like you're ready with another question. So why don't you be our last question?
What is a day-to-day life? What's a day-to-day what you do?
Sure. Yeah. So a normal day for me would be waking up in the morning. I go to the gym. We have a full gym on board, so I go to the gym and I work out, get my stretches in, and then I would go get breakfast, go watch the sunrise because my shift is from 6 a.m. to 6 p.m. And then from there, I would go to the office, checking emails, maybe take a couple tours out. We do tours to different classrooms and universities around the world. So I would do a couple of tours, and then also make video posts, make social media posts. We're also in charge of that. So making educational content for people at home. And what else do we do?
We also manage the website, so make sure we have written content to be shared with you all. And then we do a lot of sort of events on board as well. So we had a hot wing competition where we helped out and run. We do logo competitions to make the expedition logo. But a lot of it is basically you work 12-hour shifts. And so whatever you can do in that 12 hours to do your job on the ship, you do. And then outside of that is your social time. So you can go to a mood room, you can go to the karaoke room, you can call your family, you can call your friends, you can just sit outside. I think yesterday I went to go sing on the helicopter pad because it was fun.
Hula hooping. We have all sorts of activities on board because when you're out at sea for 2 months, you want to make sure that you keep morale high. And so they do those events like the Hot Wings contest and different things on board, karaoke, so that everybody stays in high spirits for the whole 2 months.
All right. Fantastic. That sounds like hard work, but also fun. There's some fun in between.
It's a great balance.
We enjoy what we do out here.
Yes.
Fantastic. All right. Kesars, this really is our last question because I know you have other school to do today, but go ahead, please.
So, have you found anything different in this sea than the other expeditions before?
Yes. So every expedition is different. So for instance, I was on an expedition 3 years ago, and the goal was to get ocean crust, which is called basalt. So they just kept wanting to get basalt, and we went to the Mid-Atlantic, which is known for having really good long layers of basalt, because that's where the Mid-Atlantic ridge is creating ocean crust. That was the goal of that one. This area, not the goal to only get basalt. If we get basalt, great, but the goal is to get mantle rock. So what we see per expedition is different, even though, for instance, Larkin and I say, we're here to get rocks and sediment. It's always different minerals, different processes that have changed those rocks and sediment. So it is different per one.
All right. Fantastic. Kittredge, Comets, and Kesars, you are amazing today. What good questions.
Thank you.
I want to give you a chance as I set you free to just give a big wave and thank you to Tessa and Larkin.
A big round of applause.
Today. I hope you have a great rest of your day. I'm going to move you back screen so you can move on with your day. Thanks for joining us. And Tessa and Larkin, I have a rapid round of questions for you just for to get a couple more student questions on the record here.
Okay.
We have a lot of questions for Walter, and I know we established Walter's asleep, so he can't answer them. So we'll
Yeah.
save the questions for Walter until later. We talked about, Ashlyn wanted to know how long it takes to get a drill ready. You said 12 hours, both directions. Taylor had a question about how long it takes to get a sample. We talked about that today. Emerson would like to know, what's the deepest your team has drilled?
So,
well, on this expedition, it's been about 3,500 meters. That's been about the average.
Yeah, that's a long way.
It can go even longer, though. I think
it can. Yeah.
The capabilities are 8,000 meters.
I feel like that.
I think it's 8,000 meters.
Or even more sometimes if we really stretch it.
Is that beneath the surface of the water or beneath the surface of the seafloor? Okay, great.
Including the water.
Okay, very good. We talked about, Kaylee wanted to know how you pick a drill site. You talked about how that's determined 5 years ahead of time. I thought your story about the internet cables going down is very interesting. Cables do actually connect us all. Gus would like to know how many sediment layers there are. Is there an answer to that question?
So technically layering is consistently happening. So like you saw that image of the sediment x-ray, each of those dark lines is a layer. So there's a lot.
You could think of it almost like a tree, like the rings on a tree. The older the tree is, the more rings you're going to have. So it means not the exact same thing, but it's similar to that. It's an ever growing kind of thing. Yeah.
All right,
so
excellent.
More than 5 at least.
More than 5. Taylor would like to know if you use carbon dating on the fossils, the microfossils.
So on the ship, no. So the ship, we do a lot more. It's like estimating. So like kind of like compare what you see immediately in the fossil to the paleomagnetist reversal measurement. Any carbon dating would be dependent on the individual researcher if that was valuable to them for their own research.
All right, excellent. Well, we covered so much today. This was such a fun tour. Thank you so much, Tessa and Larkin. Thanks to our on-camera classrooms from Kittredge. You were awesome. Thanks to the students who read the virtual exchange articles and submitted those great questions. I just get the sense we have a lot more to cover. We have a lot more to talk about. So let's do this again really soon. This was really fun. Thanks again to everybody who joined. Make sure you're checking out the virtual exchange articles being written by Larkin and Tessa. I put the link in the chat in the YouTube chat area, so you can check that out if you haven't seen it already. And I really do have to let everyone go and go on to their days, as much as I'd love to talk to you all day long. So thanks again. Great to see you. Have a great day, everyone. And we'll see you next time. Thanks for joining.
Have a great day. Bye. Bye.